Welcome to solverfy.
.54. So we're considering beta decays where the nucleus actually captures one of its own electrons. In this example, it's going to be a K-shell electron. Here's vanadium decaying into titanium by capturing an electron, and this produces a titanium that's in an excited state because it's just had one of its lowest energy level electrons sucked into the nucleus, plus a neutrino that we don't really need to worry about for this problem. And we're told this has a half-life of 331 days, presumably just as, sort of fun information. So we want to show that the disintegration energy is equal to the difference in the atomic masses times c² minus the binding energy of the vanadium K-shell electron. And it suggests that we put in bold M and MV and MTI as the nuclear masses, and then add in enough electrons to use the atomic masses. And it's a little bit difficult to handwrite bold letters, but we can use a different color. So assuming that the neutrino has a mass that we can neglect, and certainly in experiments looking at these sorts of things, the fact that neutrinos have mass is completely unmeasurable. And in fact, it took a very long time, I think until the 90s, for the first evidence that neutrinos have to have masses. Which was not done by looking at the disintegration energies of beta decays. So we use blue for the nuclear masses. So this is MTI minus MV minus the mass of the electron. So vanadium has 23 electrons and titanium has 22. If we add and subtract 22 electron masses from this, we're going to be able to use the atomic masses. So we have the mass of the titanium nucleus plus the mass of 22 electrons minus the mass of the vanadium nucleus minus 23 electrons, because we had a minus 1 electron mass, and then we added and subtracted 22. So we just, the minus 22 minus 1, you just say it minus 23 times c². So then this is what we'll call in black the atomic mass of titanium. This will be the atomic mass of the vanadium. Now, so the difference in mass energy is what we're looking for this part of this expression. Which is MTI minus MV c². And now, this is backwards, but recall that if nothing else is going on besides the masses of things getting split apart, the disintegration energy is the negative of delta M c². Now this assumes, though, that the atoms are in their ground states, because the energy is going to be different if we have an atom in an excited state. We just said that since we're sucking a low energy electron into our vanadium nucleus, that's going to leave the titanium atom in an excited state. So this isn't sufficient to account for this. And this is where the minus energy of this K-shell electron comes from, is because we've also taken out the the energy that was involved in that being in it, its ground state, or its binding energy. And so then just putting this in, we get mass of our vanadium atom minus the mass of our titanium atom times c squared minus the binding energy of this K-shell electron that we needed to borrow, and then thus leaving the titanium in an excited state. And since this looks exactly like what we needed to find, we're done.